if you recall, we have an object in the plane. We're just going to do this in 2 dimensions for now. And so that means we're going to make a picture, and it's just one rectangular array of pixels, like of values. So we can look at that as a continuous function if the underlying true continuous function is just fxy. So it's a function in the plane. We want to make a picture of that function. What we're going to do is we're going to have an X-ray source up here, as we saw in those diagrams, sketches of how a CT scanner works. We're going to beam X-rays along a trajectory through the patient, right? A particular trajectory here, and we will measure the intensity of the X-rays that emerge from the patient in that location. Depending what's in there, right, there will be a reduction in the number of X-rays that come out of the back of the patient from the number that went in the front, right? If more X-rays come out of the back than go in the front, we have bigger problems, right? Like, how do you make X-rays come out of a patient, right? By shining X-rays on a patient. That's tricky. So what happens is we know how many X-rays we put in because we tune our X-ray light bulb to a certain intensity, and we measure what the reduction in intensity is as it comes out the back. Okay, and it's going to be proportional to all the different types of tissues that the beam goes through in that patient, right? To set it up mathematically, we're going to model our detector direction here with the direction L. So it's just a distance in space, say millimeters along a line. And the angular view of this beam, parallel ray of X-rays, is going to be parameterized by theta. Okay, so for each theta, I'm going to get a whole set of these parallel lines. And which line we're talking about is parameterized by L. Okay, so we're going to wind up with a 2-dimensional function. So this line itself in the plane, in the XY plane, can be parameterized, right? And this is how that works. So for each XY point in the plane, right, it's on this line if this relationship holds, right? So it's an implicit way of saying all of the XY values that are on this line L theta, and it's along here. So it has a displacement little l and an angle theta, and then all of the XY values that satisfy that are on that line are satisfying this equation here. It's just the equation of a straight line, right? And if you like equations of straight lines as y equals mx plus b, you can just reshuffle this to make it that if you want, right? But this is how, just for the calculus and everything, it works out that this expression for that line is quite handy, okay? So let's go back to look at how we're going to integrate or measure the relative amount of absorption of the X-rays as we move along a ray through the patient. And this is called a CT line integral. So we're integrating how much absorption occurs as we pass through the patient, okay? So the intensity we measure at the detector, so that would be a single point on that L, little L line there, is proportional to this function. And this function is a little complicated, right? In that we have an amount of X-ray energy entering our path, and that's proportional to this energy density or relative energy density times the energy, right? And then the attenuation that occurs is proportional to the integration of the linear attenuation coefficient from the entry point to some depth d. Okay, so if I integrate to a certain depth d, I can calculate what the amount of attenuation will be by looking at the values of mu along that path. So mu is not going to be constant, right? It's going to go through lung, it's going to go through fat and bone and things. So this mu is a position of depth. And the semicolon means that actually we should do this at a whole set of energies, right? And just do this same calculation of this whole set of energies, integrate over the energy width. However, we're going to make the approximation that the energy of the incident X-ray beam on the patient is just equal to the mean of this energy distribution, right? So that's a fairly, gross assumption, right? In that X-rays up here above 100 kVp, behave quite differently than X-rays down here. But we're going to assume that we're just going to say they all have this energy, which is the mean energy of that set of X-rays. This actually will lead to artifacts in the pictures, okay? And we'll look at those artifacts. One source of those artifacts is a thing called beam hardening. That means the deeper you go through a patient, the actual energy spectrum of the beam changes as you go in, because you're losing more low energy photons as you pass through than high. So they're differentially absorbed as a function of depth. So that's a problem. And then the other problem is just that the actual amount of absorption that you're going to measure over that spectrum will be slightly different than what it is for the mean. That's a potential project. I don't know that I put that in there. One of the topics on the projects is dual energy CT, that is making CT images with multiple energies and what those applications are and how you do that. Another project could be, suppose I have this energy distribution and you do a simulation where you create a picture of a phantom that you create of different mu values. Just make that picture, right? But you make it as the sum of 100 different energies with the relative amounts of photons here. And then you make that picture with one photon energy right here. And you look and say, well, what's the difference between those two pictures, right? Try and characterize what happens when you make this assumption that you're using just the average energy. So that would be a nice little project. And fairly straightforward, right? So anyway, we're going to make that assumption. And so this term here actually just becomes I0, which is just a single value of intensity that is associated with the mean energy. And then this integration, say, is just, whatever the mu value is at the average energy, right, for all of these different materials. And so we're going through different materials and we evaluate mu at the average energy. So if I look at this expression, this is my intensity at my detector, right? This is the intensity that entered the patient. Right? So I can just divide the intensity at the detector by the intensity that entered the patient. And now I have a fractional number. It's a number between 0 and 1 that gives you, well, how much attenuation occurred there, just as a fraction, right? And so this number, ID over I0, is a number between 0 and 1. If we take the log of that number, right, it's going to be a negative number because it's between 0 and 1. So put a negative in front and we'll call that number just G, right? When you look at this, G turns out to be just proportional to this integral, right? Because we took the log of this thing and it's an exponential. What it does is it brings out this integral. And so now, just by doing that normalization and then taking the log, and this it's got a very sophisticated name in CT, it's called taking the log, logged data, that's what it is. Sometimes you work with raw data, sometimes you work with logged data. And if you have logged data, it looks like this. And it's proportional to the integral of the mu values across the patient. That's pretty cool, right? Because now we have like a number that is proportional to that integral of all these mu values through a path through the patient. This is our raw data, essentially, that's used for CT reconstruction, right? When we plot it up and look at it, that's what it looks like. That's fed into the reconstruction algorithm. So going back here, we have I naught coming in here, right? And then ID comes out the back, right? This is what's going to hit the detector, right? And then we can create a function here, which is G, right, at this point, which is proportional to this thing, okay? Anything else we need to know about this? I don't think so. So this function, you know, it's always positive, right? Yep.
So here, since U is a function of average energy, can we assume the average energy to a specific to always the same no matter what kind of case? Like for example, if you're sampling or doing through a part, right? You assume that for one person through that part, the average energy will always be the same. Otherwise, you will change based on every time you run the scanner, right?
Right. Yeah, what's going to happen is we're going to get this symbol here turns out to be the thing we solve for, and it's mu, right? And whether or not it's mu of the average energy or some other number is kind of, at this point, kind of irrelevant. I mean, as a derivation for what it should be, this is what we're going to assume it is. But in fact, it's just a number, which is close to, it's probably close to the mu of the average energy, but not exactly, right? So, but we are going to get estimates of this number, right? That's what our picture is going to be, right? So here's an example where we put this phantom in a CT scanner, and this phantom is something we built on a printer. This is like a resin, and it has an hourglass shape, and we filled it with contrast, and that's why it's bright, where the contrast is in the chamber. And then the resin is this CT unit here. And go back to arrow, here we go. These are pacemaker leads in the same field of view, and so they're wires basically. And we were doing this as part of a study to see if we can get rid of artifacts from pacemaker leads, right? But it's a nice, simple projection, right, of an object. And so this is the 3D rendering of the CT image that we reconstructed. So when you look at it rotating around, there's the object in 3D that we reconstructed, right? When we look at the raw data from which it's reconstructed, it's remarkably similar, right? In that when we look at the different views that the scanner obtains as the detector and source are rotating, they look like this. So it's shadows cast by that object and those leads onto the detector. And our detector, in this case, is 256 elements this way, right? And we saw that, blown up picture of the detector. So it has 256, some people call them dexels because they're actual detector elements, or, as opposed to pixels in an image. And then there's about 1,000 this way. It's actually 832, but it's, somewhere around 1,000. Okay? So these are just sets of two-dimensional pictures of the projection of this object onto the detector. And as we rotate around that object, we'll obtain about 1,000 different pictures at different angles as we go around. Okay. And from these data, this is how we're going to reconstruct our picture, right? This image here, as you'll note, that it has low values in areas behind the pacing leads, right? Because the pacing leads absorbed a lot of photons. So this, in fact, is true raw data. This is not logged data. It is just the number of photon counts seen in each detector. Okay, so it's this, ID equals I naught. So if I naught is the same at every location, then, this is the relative values of this are just the relative amounts of photons seen. The reason the photons are dark out here, so in the background where you have air, you get a lot of photons, right? It's a bright number. Here you get a low number. Out here, you get a dark number because there's a thing called a bow tie filter, which is a structure that is very thin in the middle and it gets thicker as it goes away from the middle. And that eliminates photons on the outer edges of the object, specifically in those regions in a human that you're not that interested in imaging. So if you're not interested in imaging something, why illuminate it with X-rays? So you get a very low value of the X-rays. You can still reconstruct it, but it's at a lower signal to noise. But it reduces the total number of photons that hit the patient to those in a sort of focused region. That's called the bow tie filter. When we log that data and look at it, sorry, I don't have that data logged, but I have this data logged, and this is a human, right? And this is through their chest. And so this kind of looks like a chest X-ray, right? If I go back, if I get it oriented straight up and down like that, okay, there's a spine, there's the profile of the heart. This is the patient's right side and their left side. And this just looks like a chest X-ray. That's what you would see, right? And except we get about 1,000 chest X-rays, right? We go, get them from all these different directions. You could, if you were strapped for cash, right? And you wanted a CT scanner, you could put a patient in front of a chest X-ray detector, right? So, I don't know if you've had chest X-rays, but the detector's behind you and you stand there like this and they say, okay, hold your breath, click, and they take a picture. You could put a patient just on a Lazy Susan for people, right? You know what Lazy Susan is? It's like a spinner thing on a table, or if you go to a really good Chinese restaurant, sometimes they have a really big spinning thing and the fish come by. That's awesome. Put them on that, right? Turn on your chest X-ray machine and just spin the patient. Around they go, and you could get a CT of the patient, right? Problem is you can't spin them that fast, right? Because then you start wobbling them and things like that. But it's a reasonable approach, yeah. Well, if you could spin them at a constant rate and you could just leave the X-rays on and they were constant, they didn't sort of fluctuate over time, then you're basically, every time you snap out a picture, right, 1,000 pictures in one spin or something, you'll be doing okay. There are some distortions that could happen in, oftentimes when they do this, they don't spin the patient, but they'll take a fluoroscopy machine and they'll rotate the whole machine around the patient. And the actual position of the source and the detector, depending on gravity, like when it's in this orientation, the detector's here and the source is here, versus this orientation, there'll be a change in the distance or a sag, and that'll cause distortions. But it's, in general, you can rotate the patient. So here we're looking from the back of the patient, right? Because their heart now is over here. So this is their left side. And as you can see, we're taking not just one rotation through this patient. We're taking a lot of rotations through this patient, right? Why would we be taking a lot of rotations through this patient? Well, the reason is we're taking 1 second of data, right? And the reason you want 1 second of data is a heartbeat is about 1 second. And so you get enough data to get a picture at every phase of the heartbeat, right? Back in the introduction, when we played a movie and you saw the heart beating, that was 1 second of data, right? And then you reconstruct it let's say 100 millisecond intervals or whatever, and you get a frame, 10 frame movie. Right? So that's why there's a lot of this data, right? It's just going around, 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 around. And you can imagine that each orientation, each time you pass the same orientation, you get some data. That's kind of your temporal resolution of how you can sample this 3D object, right? Roughly. Turns out you really only need 180 degrees of rotation to make the picture. So you basically can make 2 pictures per rotation, something like that. Okay, everybody clear on what this is that we're looking at? Remember, we've logged the data, so it's a positive number. Brightness now, when it's bright, means a lot of photons got absorbed, right? Where it's darker, it means the photons traveled straight. Ironically, our signal to noise of measuring the dark spots here is better because there's more photons to count. If we go to this view here, where you're looking through a long distance through a lot of patient, many photons get absorbed, and you get a kind of a noisy estimate here because you get down to actually photon counting limits, you know, of whether or not you have enough photons there. So just to go back to our math that we're going to look at, our math is in 2 dimensions. This raw data is in 3 dimensions. And so what we're going to look at is, how do I reconstruct the 2-dimensional picture that corresponds to the slice through my raw data that I'm showing you here, that is at a constant Z location. Okay, so I'm going to make actually 256 separate 2-dimensional pictures. And this parameter here, Z, is this axis. And so if I just count up, say, to Z equals the 128th row of detectors and just take all that data, then that gives me GL theta for that Z value. Okay. And then all the math we're going to look at now is just in L and theta. It is not, we're not going to look at Z. Okay. We'll just assume we can do this for each slice. Okay. Okay. So here we are back at our starting diagram, where we have X-ray beam intensity I naught comes out the back, ID. We take the logarithm, we get a number here, which is this G value. We have a whole set of those for each theta, right, as a function of position. And remember, we're going to sample this at discrete values, whatever the separation is of our detectors in the L direction. Put this on this way. And we will just sample, say, 1,000 times over 360 degrees, right, to sample in theta. Okay. That gives us a large 2-dimensional data set, right, which is G as a function of L and theta. Okay. So that's 2D. That's just a picture, right, in 2D. And our task is take that picture and make this picture, which is the mu values at each point X and Y in the patient, right? And that's the CT image. Okay, yeah.
So given like just the geometry of the problem, I'm thinking, could this be cast as like some kind of orthogonal projection problem? Or misinterpreted?
No, it is actually a projection problem, and we'll see. There's a thing called, which is going to come up shortly, called the projection slice theorem, which gives us a big hint as to how we can do this reconstruction. You can also, generally, right, when you look at this, we'll take a look at a general way of solving this, and that is, if I discretize this and I just have a big matrix of numbers, I just need to find whatever the linear transformation is to go from here to here, right? It's an equivalent number of numbers. There's an equivalent amount of information here, presumably, than here. We haven't, although this integration here, you would think, well, it does, don't you lose some resolution, some information, because you're integrating through the object, right? So aren't all of the high resolution features along here integrated out in this estimate? And doesn't that happen at every angle? So how do you recover high resolution? It turns out if you sample enough of them, right, you get enough of these, you actually do have the information to reconstruct this object entirely, right? Even though this is composed of all of these integrals through the object, right? So the first thing we're going to do, we've avoided this thus far in talking about it, but the math on this page, right? All of the L values just give you parallel lines through the object, right? So as I change L, it just moves me along to a new parallel line through the object at that theta projection. So really the geometry of the data I want are parallel lines of X-ray beams through the patient, right? So we like this geometry for our data, right? And this is L, right, in this direction. So with theta equals 90 degrees, I get one, and I set theta equals 120, I get another. So here's L this way with 90, and then 120, I get another set of numbers here, and I'm going to fill up this data matrix GL theta in this way. However, our scanner doesn't work that way, right? Our scanner works this way. And we have a point source. Ideally, it's a point. And X-rays come out in what's called a fan beam, right? Because it's a picture of a fan. So I get a whole set of theta values for each instance of my sampling along the L direction. So in this geometry, L is my distance along this detector, which catches the X-rays coming through the patient. And for each element in that detector, it has a unique theta value from all the other elements for that view, right? And so that means when I take one set of data, like I'll go poof and take a sample set here for a given orientation of the gantry, which is the source and the detector, what that does is it gives me a whole set of angles for my different L values, right? But each time I click to a new orientation, it gives me the same set, the same angle of those angles. So I will eventually fill up my GL theta space, right? It's just not filled up along these straight lines. It's filled up along these diagonals. Right? And so, but if I do 360 degrees, or actually you can see 180 degrees would be sufficient, right? 180 degrees of these. I have to do a little more than 180 degrees of these because I start missing data in the corners if I only do 180 degrees. So I have to do 180 plus 1/2 of this angle. But then doing that, I can fill up this space with sampled points, right? And I can resort them into a geometry that looks like this. Okay, so I just take these values, I look down at a constant angle and just pick off all of my GL theta values, right? So this is a fan beam geometry, and this is a parallel beam geometry. And so one of the issues in the project is to look at the difference between those two cases, and like what happens, like what are some of the things you have to think about when you're talking about fan beam geometry. Principally this one, but there's some others as well. And you can imagine if something is moving while you're taking this acquisition, that would affect you differently if you're looking at a fan beam versus this, right? When you reconstruct the parallel beams by sampling through this space, the interesting thing is that the parallel beam, at a one specific L value actually gets sampled at a different time than at another L value, right? At that same angle. And so there's a distribution of times for each one of those views. And so it makes the data slightly more complex if it's changing in time. Okay. So you can look through these two examples just to satisfy yourself that, oh yeah, I understand that this one, its center view is at 90 degrees, but it's also obtaining data at theta 0 and data at theta 120 simultaneously, right? And then these are all simultaneous. And then when I move from top to bottom, that means at a constant angle, I'm no longer simultaneous, right? So in the early days of CT, when they were reconstructing pictures, they needed to scale the values so that they were simple integers, right, with enough significant digits to make sense, right? And the mechanism they came up with was this. It's called either CT number or Hounsfield units. And so whenever you see a CT image and you load it into your DICOM viewer and you bring it up, when you put a region of interest on that CT image, it will be in these units, in these Hounsfield units. That's the number that comes out. And it's nice in the sense that water always has the same Hounsfield unit. Fat usually has the same. Blood, depending on the patient. Contrast at a specific concentration will have the same Hounsfield units. So things are reproducible. In MR, it's very difficult to say, oh, the MR value of, say, cardiac muscle is the following. If you go down to the fundamental parameters that define the NMR experiment, you can measure those and they're roughly constant, but the actual image values, totally relative, and they usually mean nothing, right? It just the relative value means something. In CT, it turns out that because everything is based on what the mu value is of water measured by your scanner on that day, right? And air, because you measure air as well on that day, you set this to -1,000, scale it, so this is -1,000, and you set this so that it's 0, right? That's how the scanner calibrates itself every day. A tech will take a phantom, put it in the scanner, push a programmed sequence that goes in there and does this calibration, right? So that for the rest of that day, the calibration is done such that water comes up as 0, air comes up as -1,000. And then everything else is measured relative to that mu value of water. So this is the mu value we measure in a patient at a specific pixel, say in blood, and it's displayed as a CT number with this fractional value of water, difference from water, times 1,000, so that you can make it an integer. Because back when they first started making these in the late 70s, you can imagine they had like many fewer bits like on their displays, right? They probably had like 8-bit displays, maybe 10-bit displays, something like that. They're really luxurious. So they needed numbers that were manageable. Here's just a list of some of the typical values, but it's more fun to look at it as a picture. Skeletal muscle, it has a Hounsfield unit value of about 100, right? So it's slightly more absorbent of X-rays than water, right? Than just pure water. If you have contrast mixed in with the blood, you can get up to 650 Hounsfield units, so even more attenuation than in water. If you look at something like a piece of calcium in an artery, like arteries often get calcified, they're up at 1,300. It's a very dense material, so absorbs a lot of X-rays. What else we got here? Fat, this is subcutaneous fat here, -120. So does not attenuate as much as water, right? A little bit less than water. Bone is 750, etc. So that gives you an idea of the sort of scale of these things. Metal, this wire that's on the patient's chest, which is probably a ECG lead that's outside the patient, is just they tag on ECG leads and it's just laying there on the chest, that's 5,000, right? Since it's a metal which absorbs X-rays pretty heavily. And then if we go down to the lower values and look at the details of the lungs, when we're looking at this, we can't really see what's down here because we don't have enough dynamic range on our display to look at these high values as well as the low values. So we go down and look at these low values down here. And in lung, we got Hounsfield units of minus 800. So it's almost air. Air is minus 1,000. Okay, and we know that's going to be true because we've calibrated the scanner that day. Minus 800, so some absorption. And you know, this in this view, normally when you send CT data that has a human chest involved, they have to take two different reconstructions to display to the radiologist. One where you're looking at stuff up here, like bones and things like that, and another when you're looking at the lungs. And that's to detect whether or not there's more water in the lungs, basically. So remember, we saw those pictures, I think, of COVID, you know, of pneumonia and things like that. It comes up very well. It shows up really well in the lungs and these things. Okay. Any questions about that thus far? It's all pretty general stuff. So we're going to go back to this concept, which is having a set of measurements, right, that I've got on my detector. I've read them off my detector, and I now want to create a map of the linear attenuation coefficients as a function of position in the patient. That's my goal. And this is a map. Say there's 512 by 512 pixels in this slice. Each pixel's dimension is about 0.5 millimeter in the X and 0.5 millimeter in Y, something around there. And it's usually about 0.5 millimeter thick. And inside that voxel, you have a value, and it is proportional to the linear attenuation coefficient for that tissue, right? That's what we're looking at here. And then those linear attenuation coefficients are just scaled into these Hounsfield unit numbers. You can just map it back to mu if you want, right? So let's look at a really simple image to start with. And this is has a field of view of 2 by 2 pixels, right? And our image will be the linear attenuation coefficients at each one of those positions. We've got 4 possible positions. I take projection data. So I take a beam of X-rays this way. And I'm sorry, this isn't a G. This is, Tom's side, it's a P, but this should be G, like the G value, so a 1. We go through this way, up P2 is the projection through there, P3, P4. So my raw data, right, that I get from my 2 projections here, well, actually 4, you know, projections through the object, I can write down like this, right? I know that P1 is mu1 plus mu2. This is just the generalization of that integral, right? Or a particular instance of that integral. P2 is mu3 plus mu4, right? P3, mu1 plus mu3, etc. So I'm just integrating through those pathways. So now I have 4 unknowns that I have to solve for, which is mu1, mu2, mu3, and mu4. If I have those, I've got my picture, right? What I've been handed by my scanner is the data P1, P2, P3, and P4, right? So I need to do that transformation from that GL theta to mu. And I write down this set of equations, which we could do for a patient. And you can put it into matrix form like this, right? That's just this set of equations in the matrix form. I've got 4 equations, 4 unknowns. So I should be able to solve for the mu's, right, from that number of unknowns. There's a bit of a complication here in that this one, well, this whole set of equations turns out is not linearly independent, right? Just given these projections, because this one can be written as the arithmetic combination of the others. So this is not a full rank matrix, that's called. So it actually doesn't have an inverse. So let's take another projection. We'll take a projection this way, right? do P5, write that down here. It's mu1 plus mu4. Now it's full rank. They're all independent, and we can do this inversion. Okay. So with those views, with the 4 views that I've taken there, I can reconstruct these 4 values. So it's all well and good if it's a small image, right? Because for 4 values, I have a 4 by 4 matrix, right? For a 512 by 512 image, I have 262,000 values, right? So this matrix would be 262,000 by 262,000. It becomes a very large matrix, right? It is called the system matrix of your system, right? Because, you know, what goes into filling out these coefficients here tells you something about your system, right? But it's just an enormous matrix to invert. And so it's pretty unstable, especially when it gets noisy. And so this direct inverse approach is really not done in clinical scanning, right? Because you wind up with a solution off in some corner. So it's as time goes on, this technique may come back, you know, but deep learning will probably completely supersede it before it has a chance to come back. So let's look at a simpler way of doing a reconstruction, which is called back projection. And now we've got a 3 by 3 example image. So I have 9 total values here. And we're going to do the same experiment. We're going to take a beam and we'll measure the amount of attenuation, right, through those 3 boxes. And it turns out there's 0 attenuation to those boxes. Go through these 3 boxes, I get a relative attenuation of 3. This is 0, 0, 3, 0. Okay. Given this data along here, I know if this is 0, I know pretty well they're all 0, but let's not go there right now. But if this is 3, what I don't know is it 1, 1, 1, right? Is the 3 in this box and these are 2 zeros? I don't know anything about the resolution in this direction with that single projection, right, to that object. All I know is that the sum of those boxes is equal to 3. And I know the sum of these boxes is equal to 3. And so we can propose a really simplistic and very fast way of doing a reconstruction. And that is, for each one of these projections, we're just going to project back from the direction it came, and we'll split up the value amongst all the boxes that are in that path. We'll say, that's as good as we can get. I have a 3 here. So when I look back across these boxes, I'm just going to split it up such that everybody gets the equal amount, right, of that projection. And so I project it all the way back to the object. And so for my first projections, if I'm projecting back this way, I get zeros across here, all ones, and zeros across here. Now I'm going to look at what happens when I project my rays that are at this angle. Well, I start with this, okay, and then I project my 3 value into these 3 boxes. So I get a 1 because it started at 0. I get a 2 because I already had 1 in there, and then I get another 1. Right. This one, we get a 1. This one, we get a 1. When I go vertical, I'm going to project the zeros on the side here, these 2 zeros, and I project the 1s back through this. I put a 1 in this box. I add 1 to this box to get 3, and a 1 in this box. And then I do the same thing from a different angle, different projection, and I project these values, and I get a 4 in the middle. So from those 4 projections, so we remember we had the 4 equations, 4 unknown in there. I get this picture. So that picture is not correct, right? I got the wrong numbers, but it's not bad, right? not that bad. I mean, you've got a peak in the middle and it's constant in the background. And so for something this small, it actually worked pretty darn well, right? And so that's naive back projection. And you can do it almost instantaneously with your data. So you get a very rapid picture. So, and back in the 80s and whatnot, when they were making the first scanners, you really could only do 1D computations on these array processors that they had. They had like, array processors that were just meant to do one-dimensional stuff. And this back projection was something you could do on an array processor really quickly. So let's look at an example of, say, a disk in a two-dimensional field of view. And so here's my disk. The true image is a circular object that's constant amplitude at a specific point and a given width. When I take my data, this would be the L direction, and theta here is, say, 90 degrees. And then for a specific set of L's, I get non-zero values that is a projection of a circle, and the projection is the integrals through a circle as we go vertically through that circle, right? And that integral looks like a function like that. That integral has a peak at the top and an edge, and outside of which it's all zero. And so that's my data. Change the orientation or change theta, and then a different L value now, I get the exact same function because the circle is symmetric. As I roll theta around, it doesn't change its look. And so I get this same data. And then for 90 degrees, at a different L value, I get the same theta. If I back project just these three views, I get this as my image. Okay, well, I've localized something here, right? There's something of a specific width, and it's at a pretty good location, right? But it's obviously, this image is not the object, because they're called streaks basically are there, and they aren't part of the original object, right? So there's some artifact of the fact we've taken too few views, and we've done this simple back projection. Right? If you take more and more views, think, well, if I just take enough views, things will get better. So you do that. So we'll take 1,000 views, you get this picture. And what it looks like is a disk in a very deep fog. So it's essentially a blurred version of that disk, right? We know from the structure of these objects that this thing has a peak at a point, right? And then it rolls off. And then you can see as we go outside the edge of the object, it continues kind of to roll off. And that's all of this stuff, right? Once that's all added up together, you get this background that it's rolling off to. So it does give you an image of the object, but a very blurry one. There's in the module section of the course for this week, I put a couple of MATLAB demos in there, and you can run those demos to look at what the radon transform, as we'll get to, does, and look at back projections and stuff like that. But we'll get there. Okay, so I'm going to go to the next set of lectures here. Any questions? Yeah? The drawbacks for the back projection are, the principal drawbacks are, it blurs the image a lot, and the final image you get is not the object, right? So it's an estimate of the object, but it's not the correct values. So we will figure out now, how do we get the correct values for the object? Eventually we'll figure that out. What time we have? Well, we got 20 minutes. So here's where we are. We get this blurry object. Oh, this is an interesting demo. This is the back projection of one view through a human head, right? Of G of L values. So this is L along here, and then these are the GL values as we project through the whole image space. And then what we're going to do is we're going to add more views, you know, like here. And then as we add those more views, the object kind of snaps into existence, right? And we can watch that happen. So I have only a couple of views here at different angles, right? And you can see kind of what's happening, right? This edge is very well resolved at this point because these projections happen to be tangent to that edge. And so it's telling you with great precision where this edge steps off, right? Because those views happen to sample that edge, right? The other edge of the patient's head, we just haven't resolved any of that yet because everything has just been integrated right through that edge, and there was no sampling of those edges, right? But as we change the orientation of our grid, you know, of our sampling grid and our source, we can fill in as we turn around those other edges, right? And details. And you can see as we, that's sort of 180 degrees through there, and then we come around 360. So we get this very nice high resolution picture. This picture is not created using simple back projection. It's created using what's called convolution back projection. And what we're going to figure out in the next 20 minutes or so is like, how do you get there to convolution back projection in order to reconstruct the actual object, right, that's there, as opposed to this simple back projection. But first, let's take a look at the data itself. So here is a very simple phantom. It's two-dimensional image in the plane. It has air holes. It has some very small contrast items here, which have slightly different attenuation coefficients than this background plastic. These simulate bone. They have high linear attenuation coefficients. This data is GL theta for this object. Okay? And so theta is in this direction and L is in this direction. Okay? And each one of these, you know, you can, for each theta value, we can just draw a line across here and look at the projection, right, through this object, which gives us this GL theta. And it's called a sinogram. So if I look at this red line and ask, well, if this is a projection of the object or integration to the object, what angle is that? Right? And now if we look over at the object, I can get some clues, right? If I'm projecting and I look at the boundary of the outside of the object, and these are different angles, then the two angles that are straight down and straight up are going to produce the widest projection, right? So that will be, this point is the widest, and this point down here, as well as that. So this could be looking from the bottom straight up, and this could be looking from the top straight down, right? Because that's where the boundary is the widest. And then at 90 degrees, when this thing gets the narrowest, that's when this edge and this edge are projected here and here, right? And so this theta is either looking that way or that way through the object, right? So can we determine? So let's put some coordinates down. L is in this direction. We'll say small to big arrow. Theta is in this direction, right? And we'll start at theta, well, 0 is here. Looks like we go through 360, right? So it's very wide. So we start vertically, right? And then it goes through one sample of direction this way, where this junk out here, what's this junk in the picture? That's this thing, right? That's the patient table, right? So when we're projecting, and this is at a low L value, so L is going this way, right? And this is narrowest, so then this junk is projecting down to here at a low L value along here. That's this one. So that has to be this projection. And then when we rotate around, we get the widest projection, go to a narrow projection again with this junk at a high L value. I look at this arrow here, so it's this one. So this corresponds to sampling this, right? With this stuff coming at high L values and this stuff coming down here, and this is the minimum width across here. So that's how you can kind of figure out with a simple sinogram what direction is what. Okay, so that's that one. This guy, the first angular view is this, right? And then this one, this angle here we know because these two features cross right here, right? And this is what happens in a projection when they cross. So they're sitting right on top of each other, right? So it's interesting, like to be able to look at the object, look at your raw data and say, where could I get in trouble with this object? And oftentimes there's things in your field of view that are very strong X-ray attenuators, right? I say the spine, we've seen that before, or a metallic implant like a hip, an artificial hip, or a pacemaker lead, or a pacemaker itself, right? And when they're in line on your projection, they can essentially occlude your view of the things along that line other than themselves. So if this was a very high attenuator, it would basically just occlude my view of all of these at this specific angle. So you get these data dropouts at specific angles, and this will cause artifacts that are called streaks. They just like cause things to splash. And we'll see some of those later. Okay, this sinogram is particularly nice in that there are very few features here and they're separated quite easily, right? And so you can see, oh, this is one of those air holes and this is a bone thing. If I have a more complex object like this, then the sinogram starts to get to be fairly complex because so many things are overlapping and those integrals become kind of complicated, right? And so you get something that looks like this, right? And as you can imagine, with a human, things get even more complex. So let's look at this object and what it looks like when we do the naive back projection. Okay, so this is just as we discussed before. We're just going to take one of our views at a specific theta, and we'll map it back onto the plane XY, right, such that I just get a constant value along each one of these lines, right, which is the line that was sampled by L. And you can imagine this pattern changes as I change my angle, but all I'm going to do is just keep adding that up in the plane, right? And so this is one instance at a specific theta of this BXY, right, which is this projection back onto the plane of our sample data G. If I take all of them and just add them up, that's equivalent to taking all of those BXY and just integrating them, or just adding them up as a function of theta, right? And I do that from a 0 angle to 180, right? And when I do that, I get this, it's called a luminogram. And it's a very foggy and blurry version of our original object, which was this thing. Okay. You can, there's also a MATLAB function in the modules for this week where you can just run this MATLAB function and take a look at what it means to be a pixel in an image and where your signal goes in the sinogram. If I'm a specific pixel, right? How does my signal add up in the sinogram? And I think 207. Do I have to stop sharing to do that? No. Okay. We'll do it at the end because I don't want to kill that thing. Okay, and so this concept is one of the, if you remember anything from the course on the CT part anyway, it would be the projection slice theorem. Just remember the projection slice theorem because it's very cool. And it's, to me, it's not obvious. But what happens with the projection slice theorem is if we start in space and I have some function that's, an amplitude as a function of x and y in space, and I look at these integrals, I'm gonna write that down. If I look at each one of these and I get a g L theta here. So I've got, it's a function of L and it's parameterized as theta. It will turn out that it is related to a sampling of the Fourier transform of this image, right? Which is not obvious just straight out of the box, right? If you say, okay, I'm going to take the Fourier transform, one-dimensional Fourier transform of this function. When I take the values of that, it turns out they are equal to the values along that angle in the Fourier transform of the original image. All right, so take the Fourier transform of the original image, I get this function, it's here. Do these integrals, get GL theta, take its 1D Fourier transform, I get these values along here of the Fourier transform of the image. And that's called the projection slice theorem. The proof of that is in the book. We're not going to do it here, but here's the equation numbers in the page if you want to go back and do the the algebraic proof of this, that it's true. But we are just going to look at it to get a visceral understanding of it right now. So in our coordinate system for this course, these are the units or the coordinate system the book uses. For what we're doing in CT, we're trying to recover mu xy in the plane, right? We have GL theta defined by that integration equation, integration of the paths, the parallel paths. Mu, or this function, has a Fourier transform, right? And it's a function of spatial frequencies, little k sub x, little k sub y, and these are in cycles per millimeter, for instance. And these are in millimeters. So what we're going to show is that, or what the slice theorem, the projection slice theorem says, is that when I take my Fourier transform of GL theta as a function of L, okay, it is equal to the sampling of this Fourier transform. This GK theta is this function along here, and it's equal to the sample of the Fourier transform of this function through this angle. And so as I change theta along here, I basically get more and more samples of the Fourier transform as I go through here. Okay. So as an example, you can look at the rectangle function. We know the rectangle function, and we know the Fourier transform of the rectangle function. So you can satisfy yourself that if I take projections through the rectangle function and I integrate, along these projections to get a GL at a specific theta, and I take that Fourier transform, do I get a sampling through the Fourier transform of this function? Right. And so you can do that for basically a projection at, say, theta equals 0, where we know that GL0, when we project it at a 0-degree angle, is just going to be a rect function, right? And when we take the Fourier transform of that rect function, we get a sinc function, and that samples the 2D Fourier space along that direction. The same thing occurs at 90. And so it doesn't seem that miraculous yet, right? That this is true, because it's just a rect, it's a 1D rect mapping to a 1D sinc function, and that it works out that they're in the right place. The interesting one is when you do it at the angle, say 45 degrees, and you do those integrals, right, to get a GL 45, right, at 45 degrees. And so we get our GL 45 and look at its Fourier transform. It turns out to be what is in the Fourier plane with the two-dimensional sinc function. Okay. And so you can work through this if you want. If you have questions about it, we can go over it in more detail. But that's just an example. You can try other functions as well. So this actually, when you're at this point and you're saying, okay, well, if I have a GL theta, I take its one-dimensional Fourier transform and I get a sampling through the Fourier transform of my object, can I not just take a lot of these, which is what we're doing, like we're taking 1,000 different thetas, right? So we're getting many of these radial samplings through the Fourier transform of our object. When if we take the Fourier transform of our data and then we plot it like this, we basically have a picture of the Fourier transform of our object. Granted, our picture is in polar coordinates, right? Because we have many more points towards the origin and fewer points as we go out here. But if I took this polar data and interpolated it onto a rectilinear grid, so for each point on this grid, I just look in the neighborhood of that point in my polar data and make a sensible estimate of what my value should be on that grid, then I should be able to make a rectilinear estimate of the Fourier transform of my object. And then how do I do my reconstruction? Now we have this estimate of the Fourier transform of the object. Just do the inverse 2D Fourier transform of this thing, and we should get the object. That should be our picture, right? And so that, given that the projection slice theorem is true, that should be a way to reconstruct that object, right? And two-dimensional Fourier transforms are cheap now, on computational systems and things like that. So it's a reasonable way to do it. So let's look, if we wanted to take the inverse Fourier transform of these data, right? How would we do that? If we were to do it, say, in straight up polar coordinates. And this is going to get us to convolution back projection. That's where we're going. If we want to do the inverse Fourier transform to get mu xy, right? Our inverse Fourier transform has this form. If G, or the Fourier transform of our object, was on a rectilinear grid, right? Kx, ky. If it was on that rectilinear grid, we just would plug it into this formula, and that's our inverse Fourier transform. However, our original data is not on that rectilinear grid. Our original data actually is parameterized by K and theta, right? So K is the distance away from the origin, and theta is the angle of that sample. So it's along these values here. So it's K and theta, right? We can make that substitution into this Fourier transform. So Kx becomes K cos theta, and Ky becomes K sine theta, and K is just the magnitude of our position in the plane. And so we just substitute those values into the argument for the Fourier transform. This is a coordinate transformation. That's all we're doing, right? And when you do a coordinate transformation, you also have to take care of the size of the differential element, which is the Jacobian, right? So the Jacobian, to go from a rectilinear dkx dky into an element that is dk d theta, it turns out the factor of k has to also be put in there as well for that rectilinear element, right? So, and you can do that just by taking the derivatives of these terms. So this k value here is an essential thing that basically is the difference between simplistic back projection and the correct convolution back projection. The actual way to invert the data using back projections is we need to take into account that when our data is sampled like this on these radial lines, we need to do this inversion, right? And so here's, analytically how this looks. We've now got our inverse Fourier transform of our data that we've taken those 1D Fourier transforms, and we can just finagle things around to move the k up here. We're going to define L as x cos theta y sine theta. It's the theta dependence of this thing up here. And so this becomes e to the j2 pi kl dk d theta with my k still here from the Jacobian. And if we look at this and do this first, right? This integration first along the k direction, this guy and this guy here, right? That gives us a new function. And we're going to call that function g asterisk or g prime L theta. And it is the Fourier transform, right, or it's the inverse Fourier transform of GL theta after you multiply it by k. So if this k wasn't here and I looked at this term here, that's just the inverse Fourier transform, right, of that gk theta that I obtained by taking the Fourier transform of GL theta. When I Fourier transform this object, right, with this k here, I get a new function g asterisk L theta. And then when I add all of those up over theta, I actually get the right image, right? So it was this term, this k term, was missing from our naive back projection before, right? And so you can think of it this way. I have my Fourier data on these radial spokes. And the first thing I do is I multiply all that data by absolute value of k. And what does that look like? That is 0 at the origin. And then it gets linearly bigger as I go out to higher frequency, right? So it's just like a tent, right? A circus tent upside down. You multiply your data by that thing, right? Right. And it's called a ramp filter, right? Because it's in Fourier space and it just goes up like a ramp, like that. And so it's kind of interesting. We depress all the DC values substantially and amplify the higher frequency values. And so that's how you make a accurate inversion or reconstruction. It's called convolution back projection, and we'll pick it up there when we start on Monday.